Hello, this is Dr. J here with another episode of my Commander X16 game development devlog. Last episode, we covered how to implement animated sprites using the Exist16 library. Although there are a lot of moving parts with the library functions we developed, we reduced the work to creating a single sprite metadata file, calling a couple of functions to load and prepare a sprite, and then a single function to animate it on screen. This is great progress, but there's still a lot more functionality we'll want to build out that will be common to many games. Next on our list is going to be custom text drawing routines, because printf is just not going to cut it for an advanced game UI. In order to build out some custom text drawing routines, we're going to be utilizing the Commander X16's tiling system. As a reminder, the X16 uses a tiling system that's fairly common to game consoles of the era, which is to say that it has two separate tile layers, Layer 0 and Layer 1, with Layer 0 being drawn behind Layer 1, and you have the ability to draw sprites in front of or behind both layers, or in between the two of them. Unlike sprites, which can be drawn arbitrarily on the screen, the tiles are at fixed positions and we have a limited range of values to choose from for how many tiles we hold in our VRAM. It has to be a power of 2 in each dimension. We can scroll these two tile layers independently, a fact that can be used to create fun parallax effects and create an illusion of depth. But, unlike sprites, the positions of the individual tiles relative to each other cannot change. In other words, once we decide how much space in VRAM to allocate to our tile layers, they become, essentially, fixed arrays in memory. We'll be getting into more depth about tiles in a later video, but for now, what's important to know is that the Exist16's text display functionality is written assuming that Layer 1 is reserved for displaying text. That's because remember that we are limited to 128 sprites, so if you used sprites to display text characters, you would quickly exhaust the allocation of sprites available to you. In order to support the ability to display potentially large amounts of text, we're pretty much forced to use one of the tile layers. This means you're not going to be scrolling Layer 0, unless you do so explicitly for the purposes of creating text scrolling effects. This does mean that games utilizing the Exist16 library's text drawing functions will be restricted to using tile Layer 0 for displaying map graphics, which does impose the limitation that you can't really use the two layers in tandem to create parallax scrolling effects. But I actually don't think this is too bad a limitation for a couple of reasons. One, a lot of games don't make use of parallax scrolling anyway. Two, and more importantly, you can still achieve parallax scrolling effects by drawing sprites in front of and behind Layer 0, and scrolling those as needed to create the illusion of depth, rather than relying on Layer 1. And to be honest, for my own purposes, that's probably how I would prefer to achieve parallax scrolling anyway. So I don't think this limitation is actually too restrictive. Okay. Now that that explanation is out of the way, let's discuss text drawing. First of all, I've replaced the Commander X16's built-in font with one of my own design, which includes every basic ASCII character. I call this a Sega Genesis-like font because I seem to remember that a lot of Sega Genesis games had a font that looks a lot like this one, to the extent that I almost wonder if this was some kind of built-in system font or something. Although I haven't been able to corroborate that, so I'm not sure if I'm just making it up. Regardless of whether my association of this font with the Sega Genesis is correct or not, this is the default font that the Exist16 library uses. Since it's built to display using the X16's tiling system, it's a monospace font, and each character is 8x8 pixels. If you had your own 8x8 pixel monospace font that you prefer to use, you could theoretically replace mine with your own by creating your own image that places the relevant glyphs in the same positions as this image, and then just converting it into a file of raw palette index values using my image conversion utility. So what kind of text drawing functions do we want for robust game support? 1. The ability to display an arbitrary string anywhere on the screen. 2. The ability to display numeric data as text so that we can display things like scores, timers, hit points, and so on. And 3. This is just a bonus, but the ability to display what is known as typewriter text or scrolling text, which is where a string is displayed one character at a time instead of all at once to give an impression of narration or dialogue, would also be nice to have. You could obviously think of more bells and whistles we could add to this list, but keeping in mind, as always, that our resources on the X16 are limited, we should probably contain our enthusiasm and stick to the basics. Items 1 and 2 alone pretty much supply all the functionality necessary to meet any game's text display needs, and item 3 will serve as a bit of gravy on top of the fundamental necessities. Alright, so let's take a look at an example. As usual, we'll focus primarily on the function signatures because that's what you need to know about in order to make use of the library, but we might go into a little more detail about the implementation than usual in this episode. So, for starters, we have exist clear text, which just removes any text that is currently displayed on the screen. And then we have initialize text tiles, which you'll have to call during the setup of your program in order to prepare it for being able to use the text display routines. So let's go ahead and actually take a look at this. All right, so we can see that it loads a file called sysf.image into HiRAM. Sysf stands for system font, and it's just an image file of the type that we covered in a previous episode, and it simply contains the image with our font face that we were looking at earlier. So we go ahead and load that into HiRAM, and then we loop through every single character, and we use copy HiRAM to VRAM partial in order to copy each of the characters to a particular address in VRAM. As a side note, you may notice that starting with this episode, all of my function names are prefixed with exist. I went ahead and added this prefix to them so that if people actually end up using this library in their own projects, having this prefix will prevent any naming collisions. Always a good thing to do when you're writing a library. But anyway, so yeah, we loop through each one of the glyphs, use our copy HiRAM to VRAM partial to grab the individual glyph and copy it to a particular address in VRAM. Now, each of these addresses is contained within a giant array. Oh, let me go ahead and bring that up right here. And the index in this array corresponds to the actual glyph that the address is for. So capital A, then capital B, and so on and so forth. And the addresses are defines up here at the top of the file. So the important point here is simply to note that we've loaded all of our glyphs into addresses in VRAM in very specifically chosen addresses that we are keeping track of. And what we then have is this big array, which I've called the text table, which maps the ASCII value or ASCII code for each of the glyphs. The index in the text table is the ASCII code for that glyph offset by 32, because the first 32 ASCII codes are just a variety of white space characters and other stuff we don't care about, so we don't include any of them, which means that we have to subtract 32 from the value of each of our ASCII codes and then use that as an index into this table, and each of these is going to point to the corresponding glyph, and from that it can get the address of the character in VRAM. And therefore, what we're essentially doing is mapping the ASCII codes of each of the characters in our font set to the location in VRAM of where that character resides, so that we can then easily display it on screen. I just thought that it might be worthwhile explaining how that works. And as you may notice, this is probably the most complicated file that we've looked at so far. It's actually even more complex than our sprite animation file was, which is kind of funny because you wouldn't think of text display as being more complex than animating sprites, and it really isn't. The animated sprites really are more complex than this. It's just that this kind of takes a lot of code because we have a lot of special tables with hard-coded values that we need to define. But anyway, moving on from there, let's go ahead and look at the rest of our function signatures. So we just call initialize text tiles at the during the setup of our program to get all of the glyphs into memory. Exists draw text is what you'll call to draw a particular string in a particular location on the screen. So you just pass in the string that you want to display, and then the tile that you want to display it on as an X and Y position. So we don't have pixel level control over where to draw our text here because we're using the tiles. So instead we have tile level control, which honestly is all the granularity that we need anyway, especially because the granularity of the tiles and our font glyphs are exactly the same as each other. But that is important to note that when you give the X and Y position of where to draw a string, you're giving that in tile positions, not pixel positions. And remember that with 8x8 tiles at 320 by 240 resolution, we have, I believe, 40 tiles wide and 30 tiles high. So that's what you want to keep in mind when determining where to draw your strings. Then we have where we start getting into the typewriter text that I mentioned. So first of all, we actually have a two-dimensional array that we use when we want to display typewriter text instead of just showing the entire string all at once, where it has a certain number of rows. In this case, I am supporting up to 10 rows of typewriter text that can be shown at a time, and up to 36 columns. And so you just populate this exists typewriter text array with whatever strings that you want to display one character at a time. You call reset typewriter counters before you begin displaying a new set of strings of typewriter text. So this just resets everything back to 0, so it will begin displaying the string from the beginning. And then for each hertz or each game iteration that you want to display another character in the typewriter text you want to show, you call exists typewriter text with the X and Y positions in tile coordinates again, of where you want the upper left corner of that text to be. And the reason that this doesn't accept a string is because it references the exists typewriter text to determine what text it is that you want to display. You can also control the speed at which the text displays this way. If you wanted to display 60 characters per second, you would just call this once per game iteration. If you wanted to display at half that speed, 30 frames per second, or 30 characters per second, I mean, you would call it every other iteration of your game loop, and so on. So kind of indirect ability to do speed control on how fast you want the text to display in that way. And then the other useful function to us is actually potentially useful for more than just displaying text on the screen. So that one is actually in my exist utils header file. And that is convert long to ASCII array. And the way this works is you just supply it with a signed long, and longs on the Commander 16 are 32 bits. I don't think there's any native support for 64-bit numbers, but honestly, in a game on an 8-bit computer or 8-bit game console, what possible use would you have for 64-bit numbers anyway? 32 is sufficient. So you give it a 32-bit signed integer, and it will then convert it into a text array, or specifically an array of ASCII codes. That distinction is actually going to be important shortly. And then return, well, actually it doesn't return it to you because it is passed in as a pointer. So it just populates the character array that you pass in place, and then it just returns the length of the resulting text string. So for example, if you pass in an integer whose value is 1, 2, 3, 4, that's 4 digits long. So it will populate the passed in text string with the actual ASCII codes for the text glyphs 1, 2, 3, 4, and then it will return to you a value of 4, indicating that the resultant text array is 4 characters long. And if you give it a negative number, it does put a minus sign in front of it as well. All right, so having looked at the function signatures for our library functions and delved a little bit more into the implementation details than we ordinarily do, but I just thought they were kind of interesting in this case and also potentially useful to know. Let's go ahead and look at the example that I have put together here. So first, I have hard-coded a bunch of strings here, which are going to populate our typewriter text. And I've also made it a couple of fixed strings, which we're going to use to display fixed text on the screen. And you may notice that these are not hard-coded strings in the way that you might expect. Like, I didn't do this. Instead, I actually have a literal array filled with the ASCII codes for each of the text characters that I want to display. Why did I do it like this? This seems kind of roundabout and inconvenient compared to just using hard-coded strings. And it is, but there's a reason I did it this way. It's because I discovered, and I don't know if the CC65 compiler suite does this universally, no matter where you use it, or if this is a quirk particular to my system, but I discovered that it does not encode hard-coded strings with standard ASCII codes for each of the characters. And we kind of require standard ASCII codes in order for the Exist16 text display routines that I wrote to work correctly, which means that we cannot use hard-coded strings and use them with the Exist16 text display routines. Instead, we actually have to craft these arrays of the actual ASCII codes, because otherwise it's going to display the wrong characters for part of our text due to the encoding being, well, not what you would expect. I mean, I can't really say it's the wrong encoding, but it's wrong for our purposes because it's not standard ASCII in all cases. So this is not as annoying as it might appear for a couple of reasons. One, if you have a game with a lot of text, you're not going to want to hard code all of your game's text in your program anyway, because then you're really going to be bloating its size in low RAM. And remember, that's painfully limited. We have like 40 kilobytes to work with. So if you have a lot of text data, you're probably going to want to put that in an external file and load it into high RAM banks anyway. And if you're putting it in an external file, you're probably going to be encoding it with the actual ASCII characters with some kind of utility or something anyway, rather than putting in hard-coded strings. And honestly, a hex editor will probably be able to translate characters into their ASCII equivalents anyway. So that's reason number one that this isn't as annoying as it seems. Reason number two is precisely so that I could just put in a hard-coded array like this with a minimum of annoyance for myself. I went ahead and made a simple little utility that you run on the command line and you just give it a hard-coded string as the one command line argument that it accepts, and it spits out a comma-separated list of all of the standard ASCII codes for the characters in the string that you pass in. So if I were to just tell it, convert for me, I am a string. Then the corresponding ASCII codes for capital I, space, lowercase a, lowercase m, etc. are going to be 73, 32, 97, 109, etc., etc., etc. So I just put in all the strings that I wanted to display through my little utility, and then copied them off the command line and pasted them into here. One note, always make sure that you end all of your strings with a 0. This is null termination. Anybody familiar with C is familiar with null terminating strings. The exist text display routines are no different from built-in C text functions in that they do expect your strings to be null terminated. And if they're not, the behavior is probably going to be messed up. So always remember to end your strings with a 0. I will make sure to include a download to my little string to ASCII utility here so that just in case I'm not the only one who would find this useful, other people will be able to use it too and not have to, make their own implementation for this, even though it's not particularly difficult to do. But just a nice little time saver. Okay, so that was kind of a lot of explanation of that. Now we get to the actual main routine, or main function, I mean. So, a few things that we're going to do in here. As usual, we initialize 320 by 240 resolution. We now have a couple of exist initialization functions to call. So we call initialize tiles in order to set up the Commander X16's layer 0 and layer 1 tiles for use with our graphics library. Here's where we call initialize text tiles to load our glyphs into VRAM. In this case, we're not actually displaying any sprites, so I've commented out the line for loading sprite metadata, but any real game will certainly actually do this line and don't need to enable sprites since we're not using them, so I could have commented that out too, but I didn't. All right, and then I, just for convenience, pulled in string.h so I could use memcopy just to copy all of these arrays of the ASCII codes for the characters we want to display into the typewriter text array so that we can then use it with our display typewriter text functions. Then we call reset typewriter counters, even though we probably don't need to since we haven't actually displayed any typewriter text, but you know, just for good form, always call this before you get ready to display typewriter text. And then we display a string message at location 3, so that's going to be near the left side of the screen, 3 tiles from the left, and then 20, which is going to be about 2/3 of the way down. And we're going to display our first fixed string. Then we enter our main game loop, and we're going to change what text we display as we loop through our game here, so that it's going to display different text as the program runs. So once the game counter is greater than 180, and since we run at 60 Hertz, that means 3 seconds in, we're going to call draw typewriter text every iteration so that we will begin displaying our typewriter text at a rate of 60 characters per second, and the upper left corner of that is going to be 3 tiles from the left and 3 tiles from the top. So it will start drawing close to the upper left corner of the screen. Then, once we are 900 Hertz into our game loop, we're going to clear out all of the text on the screen. So that's 15 seconds in. And then, 3 seconds later, we are then going to change the fixed text that we are drawing in the lower right corner of the screen. We're going to clear out this string and we're going to display a different one. And lastly, in the very lower right corner of the screen, we're going to use our convert long to ASCII array to convert the number of frames that the game has been running for into a string, and we're then going to use the draw text routine to display that string in the lower right corner of the screen. So that's just a little demonstration of how you can take numerical data, in this case a counter of how many frames the game loop has been running for, but it could also be a score or a timer or hit points or anything like that. And also note that we make sure to clear out the text in that corner before we draw it. Using this little clear counter I made, which is just a string array, or an array of ASCII codes, and ASCII code 32 corresponds to the space character, or in other words, emptiness. So why is it that I need to clear out the area where I'm going to display the frame counter with all spaces before I actually display it? Well, we'll come back to the answer to that question first, having explained what the program is going to do. And by the way, the reason I have it wait for 3 seconds before I start displaying the typewriter text is because it's always going to launch it on my other screen. And so I want to give myself time to drag the window from that screen onto the one I'm actually recording, so that you'll be able to see it before the typewriter text starts displaying. So that's why there's this 3-second delay. So let's go ahead and build our project. Oops. Right, make, not build, sorry. Brain fart. I'll go ahead and leave that in the recording so that you can enjoy a nice little laugh at my expense. This is the internet. Everybody likes to do that, right? Okay, and then let's actually run it. And I'll shut up and actually just let you watch it do its thing. So there's the first string we had it display. Then you saw it do the typewriter text. Then 900 iterations in, we clear the screen. 3 seconds later, we change the text that we're displaying there. And obviously we've been displaying the frame counter in the lower right the entire time, and you can see that the conversion of the number to displayable text is working just fine. Also, I love watching counters like this where you've got the rightmost digit going up at incredible speed, and then the further you get to the left, the slower the digits increment. I don't know. I just think that's fun. Okay, so that's all of our text display routines in action, so you can see how they all work. I think it's pretty cool. I think that this will be a nice, convenient, and easy to use set of functions for doing text display for games and potentially other programs too, though of course making games is primarily what this library is for. Okay, so let's do one more thing before we end this explanation. Let's go ahead and just comment this out where we're clearing out the area of text where we're displaying that frame counter, and then rebuild our program, run it again, and see what results. Oh, actually, in order to really demonstrate what this does, the reason that it's necessary to do this, let me actually start counting from a negative number instead of from 0. That's going to kind of show what the issue is. There, rebuild again, and go. All right, so it starts out working just fine, but you're going to see, oh, what's this? Why are there these stray zeros at the end of our counter? That doesn't seem right. So why is that happening? Well, remember that the way this works is we're actually updating what each of the tiles in the Commander X16's tile layer 1, we're updating the graphic being displayed by each of those tiles, which means that if we write out some text somewhere, like, say a frame counter, if the value of the text we're writing then becomes shorter, which is to say we were displaying a value with more digits, and then we go to displaying a value with fewer digits, then unless we explicitly set those tiles back to show nothing, or rather to show a space, then they're just going to show whatever was the last character that was being displayed there before the string got shorter, which in this case, if we start, just to show it again, if we start counting from a negative number, which means that we actually cause the length of this string to decrease, then the last thing that it was displaying in those digits was a 0, and that hangs around until the string gets long enough to overwrite it again. So that's why we make sure to clear that bit of text out before we display there to get rid of any stray characters that happen to be in the area where we want to write out our text. Just a little gotcha to watch out for. And that ended up taking longer and being a little more complicated than I thought, but that pretty much concludes the demonstration of the Exist16 text display routines. I had been planning to cover more stuff in this video because I thought that we'd get through the text display stuff pretty quickly, but at this point I think it's actually taken a while, so I guess that's going to be another video for now. Next time we're going to get into handling input. Now obviously there's good built-in functionality in the Commander X16 for doing that, but even so, there's still some extra convenience functions that we can add to provide a little bit of functionality that is not built right into the Commander X16. Again, just to make things a little easier and more convenient for ourselves. So we're definitely going to be covering that in the next episode. If we have time, we might also cover some more information about working with tiles for the purposes of actually displaying, like terrain and other graphics like that, and not just displaying text. I'll see you then.